Okay, this is exercise 1.61 in the book. Just by the way, some of the numbers might get slightly altered going from version to version. So this is exercise 1.61 in version 7 of the book. But the numbers should be relatively close always. So this is going to be exercise 1.61, proving that some of the following functions are linear. Okay, so there's 4 different functions, and you want to prove that they're linear. So I'm going to look at the first one right now. It's a function going from Rn to R, okay? And U is a vector in Rn, and the function is just defined as L of V, so V is a vector in Rn, is equal to U dotted with V. Okay, so the vector U here is fixed, and L of V is just equal to U dotted with V, and we want to prove that this is linear. Okay, so basically we want to compute the left-hand side and the right-hand side of this equality in the definition of linear transformation. So L applied to C1 V1 plus C2 V2. We need to compute what this is. Okay, I'm going to say V1. V1 is the vector. I'm going to denote it like this. A1, A2, all the way down to AN. And V2 is going to be the vector B1, B2, down to Bn. Okay, so L applied to C1 V1 plus C2 V2 is equal to L applied to the vector C1 A1 plus C2 B1 C1 A2 plus C2 B2 down to C1 AN plus C2 BN. Well, this is just what is L. What does it do? It just does the dot product of that vector with U. So this is equal to U dotted with C1 A1 plus C2 B1, and I'll skip the second row, C1 A1 plus C2 Bn. Okay, what is this? Well, I'm just going to say U. This is going to be represented. What is U as a generic vector? I'm just going to represent it with the letters, let's say, x1 down through xn. So dotted with the vector C1 A1 plus C2 B1 and this is equal, by the definition of the dot product, this is x1 times C1 A1 plus C2 B1 plus, we'll leave out all of the middle terms. Of course, sorry, that should be in the superscript. Of course, they're there. We're just not writing them all. C1 AN plus C2 BN. Okay, so what is this equal to? So now there's two things. We could either just leave it like this and compute the right-hand side. In other words, C1 LV1 plus C2 LV2. But I'm going to try to massage this to make it look like C1 LV1 plus C2 LV2. So you'll see what I mean. So this is equal to x1 C1 A1 plus dot 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 plus, sorry, that subscript should be a superscript, plus xn C1 AN plus x1 C2 B1 plus dot 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 plus x in C2 Bn. Well, what is this? This first term is just C1 times U dotted with V1. And the second term, or by the first term, when I said the first term, I mean that part. And then the second term, meaning this part right here, is just C2 times U dotted with V2. Well, what is that? this is just C1 LV1 plus C2 LV2. Okay, so this proves that L applied to C1V1 plus C2V2 is equal to C1 times L applied to V1 plus C2 times L applied to V2. Now, I realize this gets kind of messy and a little confusing when we're dealing with the general case of Rn. If you're confused by that, and even if you're not confused by that, just run through this same proof, go through this same thing, but when n is equal to 3. And then let's say v1 be the vector x1, y1, z1, and v2 can be the vector x2, y2, z2, and then u can be the vector. You can pick what letters you want. Let's say, I don't know, use whatever, A, B, C if you want to, whatever. Okay, so run through this same proof, but in the specific case when n is equal to 3. And I think that will help you understand it if you don't understand it. And if you think you do understand it, this will kind of check your understanding.